So now that we know all the basic terminology behind equations and the classifications, all of these primary or basic concepts, let's deal with the actual interesting stuff, right? Like how do we solve equations? How do we solve how do we solve a linear equation? Linear equation in one variable. Okay, this is what we're gonna start with. Okay, most of you already know how to do this, and I know that for a fact. Okay, but I need to tell you about these things, and most importantly, I want you to get rid of bad habits. Okay, I know for a fact, due to my experience, that even though you can solve these equations very well, and you can get the solution quite quite easily, some of you may have bad habits in regards to the solution of equations. And I'm going to tell you what I mean by this in a moment. So I'm going to give you 6 examples about the solution of equations, about how to solve equations, I'm sorry. And let's start. So example number 1. Let's solve x minus 3 equals 2. Very simple thing. Okay, so how do we solve an equation? First of all, what does it mean to solve an equation? It means basically to find out the solution set to that equation. What's going to be this thing? The solution set to this equation, is it going to be only specific values? Is it going to be any possible value of x? Or no value at all? Okay, so let's see. How do we do it? What is the mathematical process? The mathematical process to follow is just perform. I'm going to write it here. Perform algebraic or arithmetic. Well, I'm just gonna keep algebraic. Perform algebraic operations simultaneously. Simultaneously in both sides of the equation. Okay, this is the only thing you have to do, guys. Perform algebraic operations simultaneously in both sides of the equation. What do I mean by this? Okay, I believe most of you were told, for example, when facing this equation, x minus 3 equals 2, a lot of you were told to just pass the number minus 3 to the other side, like in this way, okay? And if it was negative, it's gonna pass as positive. It passes with the opposite sign. That is wrong. That is wrong. That's what I mean by bad habits. Okay? In mathematics, you don't pass numbers from one side of the equation to the other side. You don't do that. I'm gonna completely forbid you. Okay? This in my class, this is completely forbidden to say this word. You will never say pass. Never ever. Okay? Okay, why? Because that's not a proper mathematical process, okay? We're not passing numbers. It's not like they are objects and you pick them up and then you put them on the other side like if they were physical objects. That's not what we do. Now, of course, it's going to give me, in most cases, it's going to give me the right solution, right? It's going to, look, it's x equals 5. That's my solution. Is this the solution? Yeah, because 5 minus 3 is 2. So you may be thinking, well, if it gives me the right solution, what's the problem with saying pass? The problem, guys, is that when the equations get more complicated, this is a very simple equation, okay? You must admit that. But when the equations get more complex, that passing thing will produce bad results. Trust me. Trust me. You have to believe in me. So if you have this habit of saying passing, I want you to stop doing it. It's gonna take you a lot of time to get rid of that habit, but you will. You gotta trust me. So what do we do instead? Instead of passing, what do? We do this, which is the only, well, Yeah, it's about the only general method to solve an equation. You're going to perform algebraic operations simultaneously in both sides of the equation. Why? Why simultaneously? Well, because if you have an equation, let's say, let's keep it very simple, 2 equals 2, okay? What this means is that, I mean, this side is obviously equal to this side. You know, I feel dumb saying this because it's obvious. So if you change this side, let's suppose that you're gonna add 3. So you have this side, and you're gonna add 3. And if you do the same on the other side, the same operation, you see, then the equation is gonna kept balanced, so to speak. Okay, I'm abusing the language, but it's gonna keep it's gonna maintain the balance in both sides of the equation, right? Because 2 plus 3, which is 5, is equal to 5. You see. Another example: if you have 3 equals 3, and if you want to, let's say, divide 3 over 2, this 3 over 2, okay, that's perfectly fine. You want to divide this side over 2, you gotta do the same on the other side. You see, it's a very simple idea. It's extremely simple in its nature. So just do it. What about this? Look, for example, let's say you have 2 times x plus 1 equals 3. You see? And you say, I want to get rid of these 2 right there. What can I do? Well, with some practice, you can see that you can do the following. You can divide both sides, this side and this side, by 2. So I'm gonna do it. I write the previous side as it was. I divide over 2, and I do exactly the same on the other side. You see, I always keep my operations simultaneously in both sides. Why did I do that? Why did I divide over 2? Because what I wanted to do is cancel these 2 with these 2, with the law of cancellation, and so that I can get x plus 1 equals 3 halves. You know, I can keep this fraction as a fraction, not as a decimal. And then what can I do to isolate x, or to solve for x? Well, I'm not gonna pass the plus 1 to the other side. I'm not gonna pass it. I will not pass it. What I need to do is, if I want to get rid of this plus 1 on the left side, what I do is I subtract 1 from both sides of the equation. You see? That's what I'm doing. I'm subtracting 1. X plus 1, x plus 1. 3 over 2, 3 over 2. And I'm just doing this little thing. This is the new thing that I'm doing. To both sides of the equation, I'm subtracting 1. That is perfectly valid because I'm following this law. I'm performing the same thing, the same operation in both sides of the equation simultaneously. And when I do that, and when I actually carry out the operation, I'm going to get this. X plus 1 minus 1. This minus 1 will eat up the 1, right? They're going to add up to 0. So I'm going to get x equals 3 halves minus 1. And then you can add these two, subtract these two numbers. And you're done, right? Because you have already isolated x. And this counts as having solved the problem. You see? So I did not pass the plus 1 to the other side. What did I do? I subtracted 1 from both sides. This is the correct way to think about the equations. Perform the same algebraic operation simultaneously in both sides of the equation. And if you start thinking in this way, it's gonna take you some time, some 3, 4, 5, 6 weeks to get very used to this way of thinking. But if you really get it, if you catch the idea, the rest of the semesters is gonna be very, very easy, guys. At least in the in the solution of equations. Okay, so let's now solve this equation. What do? I do not pass the minus 3 to the other side. What I'm going to do is I'm going to add 3 in both sides of the equation. You see, I'm writing this side completely as it was before, and I'm writing this side completely as it was before. And all I'm doing is this little thing. I'm adding 3 in both sides. because I know that if I do that, this plus 3 and this minus 3, when I add them, they're going to add up to 0, and they're going to leave x alone, so to speak. And then 2 plus 3, that's going to be 5, and I'm done. Okay, and what is the solution set to this equation? The solution set is 5. Or what is my root to that equation? My root is x equals 5. You know, these are different ways to say the same thing. Okay, so that's what you do. I cannot emphasize this enough, guys. I forbid you to pronounce the word pass in my class. Number 2, 2x plus 3 equals 4x minus 1. So we have this equation. What can I do? Well, let's first have all the terms with the variable in just one side of the equation. It's irrelevant which side, but most people like to have the variable on the left side. So how can I bring this term to the other side? I'm not gonna pass the 4x. What I'm gonna do is I'm gonna subtract 4x from both sides of my equation. Because if I subtract, you see this is my side, 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 and all I'm doing is subtracting 4x from both the left and the right sides. Why did I do that? Because I know that if I by doing this operation simultaneously, I know that this thing will disappear from this side, from the right side. Let's do it. 2x minus 4x, that's going to be minus 2x plus 3. And then 4x minus 4x will be 0. And I'm just going to be left with minus 1. You see? So this operation had the effect that I was looking for, which is disappearing this 4x from the right side. But I did not pass it. I subtracted it from both sides. Okay, same idea here. What do I do in order to get this plus 3 out of this left side? What I'm going to do is I'm going to subtract it from both sides. Left side, minus 3. Right side, minus 3. Let's do it. Minus 2x plus 3 minus 3, that's going to be minus 2x. And minus 1 minus 3, that's going to be minus 4. And then I have this. How can I isolate x? We have this minus 2 over here interfering. So I may decide to divide over minus 2 in both sides of the equation. In both sides. Because if I do that, this minus 2 cancels this minus 2. And I'm done. I'm going to continue here. I'm going to get x equals minus 4 over minus 2, which is 2. And I'm done with the solution of the equation. This is my root, and my solution set is the number 2. You see? So this is what you do, guys. You are going to perform the same operation in both sides of the equation simultaneously. I know it's a little long, well, a lot longer. It consumes more time, but guess what? Guess what? You don't have to do this thing all time. For example, number 3. We have this. X over 3 minus 2 equals 1. Now, once you get the idea that you're not passing any numbers, what you're doing is performing the same operation in both sides of the equation. You do not have to write the whole thing. For example, look at this. I may start this solution by doing this. I write my left side, and I'm going to add 2 because I want to get rid of this minus 2. So I may do this, and that is perfectly cool. And then what I'm going to get is x over 3 equals 3, right? Okay, and that is perfectly okay. But I know that it takes a lot of time to do this, like to make explicit what you want to do and then doing it. Okay, can we bypass this this step? Can we skip it? Yes, it's fine. It's fine if you skip it, as long as you know what you're doing, okay? For example, the way in which I would do this equation in real life is this. Okay, I have this equation. I need to get rid of this minus 2. So I'm going to add 2 in both sides. And I do it directly. There it is. I know that if I add 2 to this side, I'm just going to be left with this. I know that. It's extremely simple to see. And I know that if I add 2 to 1, I'm going to get 3. So that's it, guys. That's all you have to do. But when I ask you, what did you do to go from this level to this level of the equation, I don't want anybody of you to say that you passed the number minus 2 to the other side. That's not what you did. What you did is, teacher, what I did is I added 2 in both sides of the equation. And that would be perfect. That would be perfect. Even if you just say, I added 2. Okay, if I ask you, what do you do to go from here to here? And if somebody of you tells me, answers, I added 2. That's perfect, guys, because we understand that you added 2 to both sides of the equation and you ended up with this. And that's okay. That's the way to think about equations. We don't pass. And I'm going to keep telling you that until I bore you to death, because it's extremely important for you to catch that idea. Okay, now we have this equation. X over 3 equals 3. What can we do next? I have this x being divided by 3. So what I can do next is the following. I'm not going to pass the 3 to the other side multiplying. That's what people say. Okay, look, the 3 is dividing. Let's just pass it to the other side doing the opposite thing, multiplying. Wrong. You're not doing that. What are you doing? What you're doing is you're multiplying both sides of the equation. Let me put the left side. You're multiplying by 3 in both sides. Left side, multiplied by 3. Right side, multiplied by 3. You see, I'm multiplying both sides by 3. Is that a valid operation? Of course. You can do the same operation in both sides of the equation, and the equation will be still a perfectly good and balanced equation. Now, why did I decide to multiply by both sides by 3? Because I know that if I do that, this 3 will take away this 3. You see? And by doing so, all I'm going to be left with in the left side is the number x. X equals 3 times 3, 9. Perfect. This is the correct solution, and this is the correct way to think about the equations. What I did not do is passing this 3 to the other side, multiplying. Okay, even if it gives me the right solution, it is the incorrect way of thinking. It's incorrect. You have to get the right solution by the right process. Okay, number 4. 5 multiplies x plus 9 plus 6 equals 21. All right, so we have this equation, a little more complex, but not really that much. Okay, how can we start? We can start doing many things. I can, for example, like I don't like this 6 over here, right? I don't like it. I want to get rid of this. So one thing I can do is, well, okay, then subtract 6 from both sides. If you want to disappear this plus 6, then subtract 6 from both sides. And I'm going to do it directly. If I subtract 6 from this thing, I'm going to get only this. And if I subtract 6 from here, I'm going to get 15. You see? That's perfectly okay. Now, what can I do next? Well, I could either multiply the 5 times the parentheses. Okay, I'm going to choose 2 ways of doing this. I'm going to make a division over here. I'm going to write the same thing in here. Okay, and then I'm going to proceed to do it in a different way in a moment. So first, I'm gonna multiply these 5 times these 2 terms. So I get 4x plus 45 equals 15. That is perfectly okay. Next, I'm gonna subtract 45 because I don't want this thing here. So I'm gonna subtract 45 from here and from here. So I get 5x equals minus 30. I subtracted for 45. And then I'm gonna divide. I'm not gonna pass the 5 dividing to the other side. What I'm gonna do is I'm gonna divide both sides over 5. You see, that's what I'm doing. And because by doing so, this guy takes away this guy. Okay, 5 over 5 is 1. They cancel one another. And I get my final solution, right? I get that x equals minus 6 because minus 30 over 5 is minus 6. This is my solution or my root, and the solution set is minus 6. We're done. Now, what other thing could I have done? Okay, remember that I left right here. It's the same as this thing is the same as this thing. Now I'm gonna do some other thing. Instead of multiplying this 5 times this binomial, I'm gonna divide both sides over 5. Why? Because I wanna cancel this 5. I don't want it here. I don't want it. I wanna make it go away. So how can I do this? Well, by dividing by 5 both sides. Because I know that if I divide over 5, I get that this guy and this guy cancel one another, and I get this. X plus 9, which is the only thing that remains, equals 15 over 5, which is 3, you see? And finally, we subtract 9 from both sides, and we get this. If I subtract 9 from this side and from this side, and I'm done, you see? So, which is the same as here, right? So this is a common question. Like, teacher, my process is different from my classmates. Who is right? If both of you are getting the same answer, okay, uh, both processes are okay. If you are working a problem and then some of you follow some process and some other of you follow another process, both processes or both methods can be perfectly fine. There are several ways to solve a problem and get to the same solution. Okay, I don't want you to understand that there is only just one way of doing it. There are many ways you can do. For example, in here I multiply 5 times this binomial, I get this, and I continued. And in here what I did is I divided by over 5 right away. Which one is better? No one. Okay, not one is better than the other. It's the same thing. Okay, and I'm gonna now close the lesson with an example of an identity and of a contradiction, or an inconsistent equation. So what if I give you this equation and I tell you, please solve this equation? Give me the solution or the root of this equation and write its solution set. Okay, so let's start to work it out. I'm gonna decide first to multiply these 2 times this binomial because I want to and because it's possible. And then, okay, we have this, and then we have 1 plus 3x minus 7. Well, I can put together these two things. So I'm gonna get 3x minus 6. Okay, that is the first thing I wanted to do. And then I can put together these two things. 3x minus 6 equals 3x minus 6. And we can see it right away, guys. We can see it right away. Look at this. I'm saying that 3x minus 6 equals 3x minus 6. Of course. Okay? This is obvious, right? So if I have some expression and then an equal sign and the same expression, well, that is clear. And what I have arrived at is this is an identity, okay? Because if you continue, okay, let me actually finish up the whole thing. Because I want it to be more robust, more consistent with this. Let's add 6 in both sides. I'm gonna add 6, so I'm gonna get 3x equals 3x, right? I added 6 to here to here. And now I'm gonna subtract 3x from here And from here, I'm going to subtract 3x. What am I going to get? I'm going to get 0 equals 0, which is true. This is always true. 0 equals 0. That's a evident uh, true statement. So when you arrive at something like so, something that is true, always true, always true, then what you can conclude, the conclusion is this. Conclusion, that the equation that you started with, equation is an identity. It's an identity, okay? Because I arrived by starting here in my equation, which is an identity, and then by following some process, as long as my process is correct, and if I arrive at a statement which is always true, always, no matter what that means is that my original equation was an identity, which is, like I told you before, is an equation which is satisfied for any possible value of x. If you want to make the experiment, put any x in here. For example, if you want to give x the number -5, put -5 here, -5 here, and -5 here, and your equation will be satisfied. Okay, you don't like -5. What about 17? Okay, put 17 here, 17 here, and 17 here, and your equation will be satisfied. Put any number. It doesn't matter. Put it here, here, and here, and your equation will be satisfied. So what does that mean? That my equation is an identity. And what are the roots of my equation? What are the roots? Any value of x is a root. And what is my solution set? Well, okay, I'm going to introduce you to another thing. The solution set is this. Okay, we're going to write this. When the solutions are all the numbers or any number, then we're going to write this. And this means that the solution set is equal to the real numbers. I hope I don't confuse you with this. The real numbers. This is the symbol to represent all the real numbers. All the numbers that you know. Okay? It's like a big box that contains all the numbers. So the solution set is all the real numbers. Any number is okay for this equation. And finally, an example of an inconsistent equation. Number 6, an inconsistent equation. What if I give you 1 plus 4x equals 4x minus 3? And I tell you, please solve this equation. Okay, you're going to grab pencil and paper, and you're going to start to work out. Okay, so there's nothing to do here. And in here, I may multiply the 4 times this binomial. I'm going to get 4x minus 12. Okay, and then I observe that I have 4x here and 4x here. So I may decide to subtract 4x from both sides of the equation. I'm subtracting 4x because it's a valid operation, right? So I'm going to get 1 plus 4x minus 4x. I'm going to get 1. And equals 4x minus 12 minus 4x. I'm going to get minus 12. Right? Okay. Now observe your final conclusion. You're concluding that 1 equals minus 12. This is evidently and patently false. False always and for eternity. 1 is not equal to minus 12. So when you start with an equation that looks as though you can solve it, right? But when you look at this equation, you at first sight you may not notice anything wrong with this. But if then you start to follow a logical process carefully, and if all of these processes in between are perfect, and you arrive at something like this, something that is obviously false, like 1 equals minus 12, or 2 equals 0, false, or minus 3 equals 1/2, false. If you arrive at a false statement, what that means is that your equation was inconsistent from the beginning. This is inconsistent from the beginning. The person that wrote this equation was not careful, or he is trying to solve an equation which has no solutions. Okay? And so what is my conclusion here? What am I going to write in the exam or whatever? Okay, what we say is this. there are no solutions to this equation. There are no solutions. You can say it in many different ways. There are no solutions. There is no value of x which satisfies this equation. The solution set is empty, so you leave empty. You leave the box empty. Another way to say this is this, guys. This thing and this thing means the same. Solution set equals empty, empty set, and solution set equals the empty set. This symbol that looks like a zero. A lot of people draw the zero in this way, which is wrong. This symbol is known as the empty set. The empty set, which is a set that has no elements, right? It's got nothing inside. Just like in here, it's got nothing inside. It's an empty box. Why? Because no value of x, when you put it right there and right there, no value of x. It's not possible that you find a value of x that will satisfy the equation because it's inconsistent. So I'm gonna stop it right there. That was enough information for you to simulate. And now let's go to the exercises. What I want you to do, guys, is open up your book from Laoni on page. Let me tell you what page. Give me a moment. Okay, on page 139. 139. And that, yeah, that's on that, only that page, the learning activity number 4. You have two exercises, exercise 1 and exercise 2. You're gonna do both of them, and the only thing I don't think it's necessary to perform is the confirmation of the equations. The confirmation of an equation or the solution of an equation is something like this. For example, I'm gonna do it very quickly. If I give you this equation, and then you go like, okay, the root is quite clearly x equals 2, and then you go like, okay, let me confirm my solution. You put the solution in the equation, and you go like, okay, 9 equals 9, okay, confirmed. My solution is confirmed. This is, I mean, it's a good idea if you want to really confirm what you're doing, but if you're pretty certain about what you're doing, you do not need to confirm, okay? This is only confirmation. It's not a necessity when you are solving an equation. So it's up to you whether you want to confirm your solutions or not. I leave that decision to you. I'm not gonna require it. That's what I'm saying. I'm not gonna require it. So in those equations from learning activity number four, they ask you to confirm. But I don't want you to do that. If you want to do it, that's fine with me. But I'm not gonna ask for it. So that's it, guys. Remember, no pass. We don't say pass. This word is the devil in algebra, okay? Try to get rid of it as soon as possible. By second semester, I want all of you to stop saying this word, okay? So thank you, guys.